In what we're doing over the next bit of time, it's going to become important for us to know how to do integrals. And so these series of lectures are going to attempt to capture the basics of how to do an integral. We've already talked about what a derivative is, and a derivative gives you the rate of change of a function. It gives you a new function, which is the rate of change of your original function. In calculus, that's usually represented by saying that f prime of x, the f prime represents a new function, is the derivative of the original function. So this might be, for example, d dx of f of x. This d dx we call the differential operator, and that means to do the operation or the process of taking a derivative. And the act of taking a derivative creates a new function, f prime of x, based off of the properties and behavior of the original function. And from a physical standpoint, we think of that then as f prime of x is going to give the slope or rate of change of the original function f of x. So it's a mathematical operation. When you have a function and you do the derivative of it, you get a new function. Now in mathematics, it's often the case where if you can do something to a function, you can undo it. There's the inverse of the operation. So for example, if you take the sign of a number, you can get back the number by taking the inverse sign. Or if you take the exponent of something, if you exponentiate something, you can take the inverse function of that, which would be the logarithm, to get back your original answer. Square root, things like that. So the opposite of a derivative is an integral. So the mathematical operation of taking an integral is the inverse of a derivative. The notation is slightly different then. If we look at this particular function that I've written above, and if I write f prime of x equals d dx of f of x, we can multiply through mathematically and see that we can rewrite this as f prime of x dx equals df of x. Now, what I can do is I can do the same operation to both sides of this equation. So I can actually put in an integral sign on both sides, meaning do the integral operation. That's the antiderivative of each side. And so now I can redo these. Well, I can't do the derivative of f of x, but I can do the derivative of the differential f of x, because these two things are exact inverses of each other. The integral undoes a derivative. So that means this side just comes back to the function f of x. And so the integral of f prime of x dx is f of x. And a lot of people are very confused as to why this little dx is in there. What do you do with it? Well, you'll see that by looking at it this way, as this differential operator term being multiplied through, it is the thing you're taking the integral with respect to. Same thing as when you were originally talking about derivatives. You were taking derivatives with respect to a specific variable. Here you are taking the integral with respect to a specific variable. Now, just like the derivative had a interpretation as the slope of the original function, the integral has a physical representation or interpretation as well. If I were to take a graph of a function, let's take x squared constrained from 0 out. If we had that particular function, so I can write this in functional notation as f of x equals x squared. I can now find the integral of this by saying that I'm going to get some new function, we'll call it g of x, is equal to the integral of f of x dx. So that would be the integral of x squared dx. And here you'll see what I did is I substituted in what my f of x was. Now I would need to do that integral. And we'll talk about that a little bit later. Here I'm going to go ahead and do it. G of x would be x cubed over 3 plus a constant. And we'll come back to why this a little bit later. The mathematical interpretation of this is that I have now found for this particular value of x, g of x represents this area here. So this area underneath the curve, between the curve and the axis, from 0 out to my value of x. That is the physical interpretation of what the integral means. The integral will give me the area under the curve. The other interpretation of that is that it is doing a sum total of all of the change. So an integration is a summation. If I were to look in closer detail at that function, if I were to break it up into a few little steps, let's say that I was to break it up into 4 steps, I can simulate that one of these steps as a little rectangle where the height of the rectangle is equal to f of x and the width of the rectangle is equal to some value delta x. And in this case, delta x would be the same for each of these boxes. And if I divided up my total width by 4, then delta x is going to be the total width divided by 4. And so if I wanted to approximate the area under this curve, I would do f of x sub 1 times delta x plus f of x sub 2 times delta x plus dot 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 f of x sub n times delta x. Oops, delta x. I could add up those rectangles. And you'll notice that by approximating these things with finite rectangles, I'm overshooting the area by that much. And I would do the same thing if I drew the next rectangle. I would overshoot by that much again. So you can see this is not a very good estimate. It's okay. It's better than just simply guessing, but it's going to overshoot by a lot. What I could do is I could improve the amount that I'm overshooting by making those rectangles narrower. So the area beneath that curve can be represented then as the sum for I equals 1 to n of f of x sub n times delta x. And as if I did, 10,000 rectangles in that area, I could get each little tiny step would be very small. Delta x would be very small. And I could actually get a pretty good representation of what the area under the curve is. This is, in a way, one of the ways that computers are used to calculate those areas. But I can now get the exact representation for the area by saying that I take the limit as, you can write this 2 different ways, as n goes to infinity of the summation of I equals 1 to n of f of x sub n delta x. If I let there be an infinite number of bars, then the width of each bar is going to become infinitely small. We learned in differential calculus that when the width of the bar, the delta x change, when delta x gets infinitely small, we call it the differential value dx. So this limit then, a, the area under the curve, can now be rewritten as the integral of f of x dx. And so you see that summation is synonymous with integration. Integration is an infinite summation. It's a summation or an adding up of the area of a little rectangle, a little rectangular slice that is infinitely narrow, and we're going to add up an infinite number of them. The really great thing about calculus is you end up with a finite answer out of that, which I think is always amazing. So when we're doing integration, we're really thinking of what's the sum total effect of the process we're working on. That's why when we're doing electric fields and things, we like to think of distributions of charges as a continuous of an infinite arrangement of infinitely small point charges, and then we add them all up because we know that the total field is the superposition of the field of the individual particles. If we have an infinite array of infinitely small ones, we can find the total field of continuous charge distributions. Okay, so in the next piece, I'll talk about how to actually do those integrals now that we know what they mean.